All right, I am Jax Matz, for those of you who don't know me, and I will be doing my independent quest project on subatomic particles. Subatomic particles are smaller than atoms, and there are certain terms that describe them. They have the qualities they have are charge, spin, and mass. Mass is the easiest. You probably were taught it a long time ago. It's the amount of matter in a given particle. Next is charge. Charge would be how the particle reacts when the electromagnetic force acts upon it. So you can have negative charge, positive charge. Like charges repel and opposite charges attract. The greater the absolute value of a charge, the more it reacts to the electromagnetic force. Then you have spin, which is the angular momentum of the particle. So there are many subatomic particles, and so they need classifications of them. So they use two major classifications would be bosons and fermions. Fermions are your mass particles like quarks, which make up neutrons and protons, and electrons and neutrinos. And those are actually separated in two different groups. Electrons and neutrinos are called leptons, and quarks are just their own thing. They're quarks. Then on the other side, you have bosons. Bosons are force-carrying particles. So, for example, the photon, which is a boson, carries the electromagnetic force. There's four forces, right? Two of which are kind of united, asterisk, right? You have the electromagnetic force, which we've already said, that is the photon. Then you have the weak interaction, or the electroweak force, or the weak nuclear force, whichever one, they're all the same thing. Now, that is the force responsible for radiation. It is essentially repelling apart atoms. It's also what causes like charges to repel and opposite charges to be attracted. They're force carriers. There you have the W boson and the Z boson. The Z boson has no charge, and it's carrying a force, obviously. And then you have the W boson, which has either a positive charge or a negative charge. Now, what I haven't explained yet is there are antiparticles, which every particle has its own antiparticle version. You take an electron, you make it an opposite, you get a positron. Opposite of any given quark would be an anti-version of that quark. Antiproton, antineutron, right? So the funny thing about the Z and W bosons is a positive W boson acts as the opposite, the antiparticle, to a negative W boson. And a Z boson is its own antiparticle, even though it has no charge. An antiparticle will always have the same mass, but different charges, or same mass and spin, but different charges than its counterpart. Moving on, so that was the electroweak interaction. Then you have the strong interaction. This is what binds quarks together. We haven't got there yet. And it's incredibly strong over short distances. So, very strong, which is why, hence, strong force, strong interaction, strong nuclear force. However, it falls off exponentially, which is why radiation between protons and neutrons occurs, but why quarks are always glued together. Quarks are never found alone. The last time, I believe, was at a couple thousandths of a second after the Big Bang. There was a quark plasma, and then they paired up. Now, the boson for the strong interaction is the gluon, and the gluon is what is connecting the quarks. Finally, we have gravity. Now, the funny thing about the standard model, which is the right here, as you can see, this is the model for elementary physics, and it consists of all the particles that cannot be broken down. So photons, quarks, leptons, etc., right? Now, there is actually no boson for gravity. There is a proposed thing called the graviton. It has yet to be observed, so we cannot say for certain. So that's one of the mysteries of the standard model. Now, moving on, there's a very special boson, the Higgs boson. This is incredibly elusive. It was called the God particle because it was so hard to find. And it is what gives mass to everything. The fields essentially every particle, um, every particle and every object has a certain field. And how that field and how much that field interacts with the Higgs boson field is what gives it its mass. Higgs boson was first proposed, when was it, 1964, and was later confirmed to exist at the Large Hadron Collider in 2012. So, long time there. Now, going over to fermions, I'm going to go over quarks. So quarks have something like, well, all fermions have generations, which are like sets of particles with similar charges and the same spin, right? All fermions have a spin of 1/2, and all bosons have a spin of 1. So, the quarks come in 3 generations, and there are different sets for them. This is the down quark set. You got the bottom quark, the strange quark, and the down quark. Now, opposing them are the up quark set, which you have the top quark, the charm quark, and the top quark. They essentially occur in pairs. Imagine them as married couples, right? You have the grandparents, you have the parents, and then you have the kids, the siblings, right? So the down quark and up quark are what compose both neutrons and protons. Now, there are a lot of key differences between the two. They both have the same spin, but they each have different masses, right? So the down quark is bigger than the up quark. And all of the up quark set, they have a charge of 2/3, and all of the down quark set has a charge of -1/3. So if you do the math here, 2 down quarks and 1 up quark would cancel out, creating a neutron. And 2 up quarks and 1 down quark you'd subtract 1/3 from that, and you would get a proton that has a charge of +1. And moving up generation, you're going to get more massive, but the charge always stays the same until you reach the very top of the quark ladder, the generation ladder, and you have the top quark and the bottom quark. These are the heaviest, and they decay very, very, very quickly because of their immense size. Now, the funny thing is, the top quark is over 40 times more massive than the bottom quark. The standard model does not explain this. Another mystery of it. Each time the quarks decay, they go down a generation, hence like the generations, right? But the thing is, their decay is facilitated by the W boson, right? This weak interaction. So no matter what, the W boson has a charge. It could be negative, could be positive. And when this charge interacts with the quark, causing them to decay, this causes them to flip in charge. So the top quark would move down a generation and then to the opposite charge. So it would go over to the strange quark because top quark has a charge of 2/3, and strange quark has a charge of -1/3. Then strange quark would decay into up quark because it has a charge of 2/3, strange quark, etc. Right? You get the whole thing. Quarks are pretty interesting because they're obviously what makes up everything. These bottom ones are incredibly stable, and they don't decay, or they haven't been proven to decay yet. So when these two interact, obviously, you get the neutrons, protons. There are many other. And moving on, actually, we have these guys over here. So these are all examples of hadronic particles. So hadrons are composite particles. Think of them like that. And you have 2 different types of hadrons. You have the mesons, which are composed of 1 quark and 1 anti-quark, right? So you could have an up quark and an anti-up quark, and that would create 1 meson. Then you have baryons, which are composed of either 3 positive or 3 normal quarks or 3 negative quarks, or anti-quarks, sorry. So neutron, proton, these would be baryons. The omega particle these are just examples of other baryons. You have the omega particle, which is composed of 3 strange, and you have the lambda, which is composed of an up, down, and strange. Now, there are countless others, but most of them are very unstable and decay almost instantly. So, when these interact, they actually create, like neutrons, protons. You get like a gravitational field, which pulls in electrons. So, transition. Electrons also come in 3 generations, and they're part of the lepton family of fermions. There are 2 different types of leptons. You have electrons and neutrinos. Each have 3 generations. So the electrons, you're going to move up each time, right? You have electron, which are the smallest. Then you have the muon, which are the second smallest. Then you have the tau, which are the largest electron. Each time you move up, they get more unstable, just like with quarks. But they decay actually surprisingly slow, like when you're looking at other particles around the same size, moving up, because their decay is facilitated by the W boson, just like the quarks. Most are actually not facilitated by the W boson, and the W boson is slower to decay. So, therefore, slower to decay than most other particles. Electrons are what are in clouds outside of nucleuses of atoms. Now, what I think are very, very interesting particles are neutrinos. Neutrinos are created from solar radiation, and you got 3 types. You got the neutrino, the muon neutrino, and the tau neutrino. So same pattern there. Tau neutrino is the heaviest, neutrino is the smallest. You could also call the neutrino the electron neutrino, whatever. Neutrino's simpler though, so that's what I go with. Now, the fun thing about neutrinos is they are inconceivably small. Even the heaviest, the largest, the tau neutrino, is orders of magnitude smaller than the electron, which is minuscule compared to a proton, right? So this gives them an interesting property of passing through the gaps in matter. They could pass through holes in quarks, right? Because when you have the gluons there's going to be empty matter in between, which means they could pass through a light year of iron without ever slowing down or colliding with anything, which I find very, very interesting. So it's incredibly hard to detect them because obviously they're pretty much indetectable. They go straight through everything. So it took a long time, and in order, the instruments required to see them, they have to be deep underground in complete isolation almost. So anyways, I'm going to move on to the standard model over here. I don't know if you can see it very well. So the standard model is, like I said earlier, what gives us everything, all the knowledge compiled into like one basic table, right? So this has pretty much all the, not subatomic particles, fundamental particles on here. So we have quarks, leptons, etc., right? And it's very, very complete. It explains almost all the forces except gravity, explains how mass is created. However, there still are some like gaps in it, right? So we don't know why antimatter died out and matter went on to exist in greater numbers. We don't know why there are only three generations of fermions. It's quite strange. And that leads us to... the words are going to come. Theoretical particles, there we go, sorry about that. So theoretical particles are very interesting. You have the graviton, which we've already discussed, the gravity particle. And then you have preons. So quarks were discovered because 2/3 of the time, one face of a neutron would show, even though it's revolving at the same rate. So that's kind of strange, which resulted in them discovering quarks, right? Now, they're kind of noticing the same thing with quarks. The charges just don't line up. So preons are essentially like quarks of quarks, if that makes sense. And there should be, according to the theory, 5 preons in every given quark. Now, I like this one a lot. It is symmetrical particles. This one is quite interesting in my opinion. Basically, supersymmetry says that for every boson, there is a fermionic particle, and for every fermion, there is a fermion or a bosonic particle. So flipping the script a little bit there. So you would have the gluon fermion and the gluon boson. Again, all theoretical, skeptical, nothing confirmed there. And also, dark matter and energy could be explained by axions, which are another theoretical particle. They are a type of boson, which explains why they are almost undetectable, because bosons are very hard to detect because of their duality. Think of it as like how a photon could be a wave or a particle, pretty much the same thing with bosons. Bosons are also very unstable and last fractions of a nanosecond. So axioms are what would facilitate dark energy, dark matter. That's what makes them up. There are also tachyons, which move faster than light and therefore move backwards in time, which I also find pretty interesting. So if you have any questions, let me know now. This is the end of my presentation. Thank you for listening. How long?
Great job.